Next speaker is a poster winner prize from the previous meeting, Boston. He's a postdoc from Birmingham, Ingelheim, a member of MD Task Force, also a core developer member of the OpenFE. He's going to talk more about OpenFE. Welcome, Benjamin Ries.
Yeah, thank you. And before someone asks, this is also my third time to make this session full. And I'm very happy to be here on this great format for a chemistry meeting, and great that I can also talk here. Thank you for that already. So I want to talk to you, of course, about OpenFE. And I have a focus a bit here on tools for how we plan free energy calculations, and I also want to link it to industry applications. Hannah today actually already gave a great talk about OpenFE and how the environment OpenFE works, what are the goals, what are the different aspects that we have there. I want to add to that a bit like two example cases where we do exactly what she said, developing, here we go, developing the single modules and then putting them together into pipelines and then using them in drug design projects. With that being said, let me give you a quick overview on the current workflow that OpenFE is providing. So we have a very simple idea on how you could calculate RBFEs, and this is exactly what Hannah showed you earlier. She showed that to you in the 3 CLI commands. In the first run, you try to set up your calculation, you try to plan which transformations you want to calculate. Then you go into a simulation phase where you actually really do the alchemical transformations in simulations. And after that, you go into an analysis step. And as Aniket, for example, already mentioned, in Pharma, you often do these benchmarkings in order to see how well your free energies that you calculated are useful for your project. And if they are useful, you basically go to this final step and go beyond what you could benchmark, for example. And in my talk, I want to focus on this setup calculation phase, because this is an essential step, actually, where you can save a lot of calculation time. So what do we actually want? OpenFE per se right now wants as an input a modeled protein ligand complex. So you give us the coordinates, and then the rest is kind of happening. And in this phase, as I mentioned before, you want to plan basically the transformations you want to calculate. And as a result, you should have an efficient strategy to do these calculations. So, but how does those strategies actually look like? So the strategies, in our case, we talk about a transformation network, which is the plan of transformations that we want to calculate. We have these beautiful arrows here, which are atom mappings that are the transformations. And they are represented by this mapping that basically indicates the change that you are going to apply. And then we have the score, which is a quantity that tries to estimate the difficulty of this transformation. And with all these components, you actually already see that you can basically go to Graphland and do an efficient algorithm on how to calculate those transformation networks. In the first step, let me quickly just say one thing. So all the things I'm talking about in this talk will be about hypertopology approaches. This is indicating why we are so interested in atom mappings, for example, because what we need to do is we need to find automatically this core region in the best case, such that we can put 2 ligands onto each other or 2 molecules onto each other and represent the core region by one set of atoms. And then here there's the dual topology regions, where you then start to sample those very different parts of the molecules with different coordinate sets. Bottom line, we need to find this core region. And for that, we have 2 approaches. So one is LOMAP, that was already explained by Hannah earlier. LOMAP is, I want to emphasize this again, is a subgraph isomorphism solver-based approach. So this means actually that the MCS is found in a 2D topology way. And then we can put additional rules onto that and also add in 3D information. This is the one atom mapper that is implemented in OpenFE, and the other implemented atom mapper right now is actually Cartograph. What does Cartograph in comparison to LOMAP? Cartograph kind of turns the things around. So we don't do 2D first and then go into 3D. No, what we do is we start with 3D actually and try to shortcut the algorithmic cost here with that. So if you give us two well-aligned ligands, this is an assumption we definitely take, we need those well-aligned ligands, we will calculate the full distance matrix of all atoms. This is, of course, not necessarily useful because many of those distances are not really meaningful to us in this mapping process. So we basically cut all down to this, with this cutoff of 0.95 angstroms, and then are basically left with only a very sparse graph that we can solve here. In the next step, we use a linear sum assignment optimization. So this gives you the perfect atom assignment for this graph here, which is basically visualized here with this green. What is the tricky part here? So I mean, these cases here are trivial, of course, as you can see, but then you have these ambiguous phases. Here, for example, this white atom could basically go to the blue one or to the other blue one. And this is even also a very simple choice, but then you have connected choices. And this is exactly what our algorithm is, that is basically implemented in SciPy is solving here. After that, so we have here the raw mapping. Now we go into 2D, and we need to, first of all, apply certain rules. As a default rule, for example, we don't allow ring breaks to our atom mappings. But also what we need to do is we need to find the so-called core region, because we don't want to have disconnected mappings, because this might lead to any artifacts that you could have during the simulations. And that finally is then our mapping. Woohoo, we made it. With that, what are problems that we had with LowMap, for example? Hannah showed you already the stereochemistry case. So I'm now going into the symmetry breaking case, where you basically here, what you see is, on top you have the alignment of the molecules, so this was the input. Here you basically see the overlap of the coordinates, and immediately you might spot this yellow-bluish overlap here, which is weird. And this is due to the symmetry in the MCS problem. So what the algorithm basically does, it assigns this yellow sphere to this yellow sphere, and this translates to rotation of the full ring here, and that basically alters your binding mode that you predefined. If your binding mode was important, then you lost it possibly here. Cartograph doesn't do that by design, because we try to minimize the distances of the atom mappings. This is how the algorithm was designed, and therefore we get here actually a lucky solution on this. We did that in a more quantitative way with multiple mappings overall, and what you basically can see here now is a quantitative result of what I just showed to you. So shape matches are quite similar-ish, I would say, because the rotation here is not a thing that you will see very loudly, but the mapping armistice is something you very clearly see. So in green here you have cartograph, and in the other colors we have the two variants of LowMap that we chose. With that, where are the limitations? I already said that you need very well aligned molecules for this. So here we have now a data set or two molecules which are not super well aligned, I would say. And what you see is LowMap doesn't have a problem with that, because we go via the MCS. Who cares? We see the topology, it works. Cartograph, on the other hand, now has problems and starts to only map one ring, which is well aligned. So this is one limitation of our approach. And so Cartograph, I would call it an option, but it doesn't solve everything, of course, like any method. The other aspect that already came up in Hannah's talk was actually that Cartograph is very fast, and this is true. Because we don't do the MCS sampling, we get now here for these very simple data sets with small numbers of molecules and rather low amount of atoms, we actually get very similar results between LowMap, which are here 26 seconds, and you have Cartograph with 8 seconds. That's very similar. Nevertheless, if we go to larger data sets, we see, okay, now they start to diverge. And so with the HIF2A data set actually already, you can see Cartograph is able to do this in a minute, the full data set, and the LowMap variants actually need 11 minutes. And now we can go to more extreme, actually, if we want. And this is now a TRIC2 mutation that we started. So we just did one mutation, a lot of atoms, of course, and the LowMap algorithms never converge because they were also not designed for this. This doesn't make sense with LowMap, actually. But Cartograph is able to do this one case in 2 seconds, which is, I think, quite impressive and might outline future usage of the atom map, actually. With this being said, we also saw Hannah's benchmarks that she did actually with cartograph versus LOMAP on the public data set. That was pretty cool. I'm now going to show you the beauty of my position and the duality of it. I could now use in-house data sets of Boehringer and test this. So we compared here now OpenFE with cartograph versus an in-house workflow that we have. And we have these beautiful ABCDEFG systems in-house that we use for benchmarking here. So first, we see the RMSE. And this RMSE, basically, if you think about the bootstrap arrows, shows you that both approaches are super comparable. Going to the next step is, can we separate the good ligands from the bad ligands with class accuracy? What you see here as well is, again, they both perform very similar. And in the last step, we tried to check out the Pearson correlations. And most of those cases are very similar, except this one case, which is due to the data set. Because it's very, so the free energy experiments are very dense around 1 point. So you have a large error bar on this side, and this is giving you weird results here. What does this show you? This does not show you that everything is beautiful and everything is the same. This just shows you the potential of OpenFE on real data. And I think that's basically the message that should come across here. With this, let me sum up the cartograph part. So what we need is well-aligned ligands. We basically, when we use cartograph, have minimal position deviations. Cartograph is very fast, and the last part that I maybe did not make too clear is cartograph is very flexible. So you can add different rules to the mappings that you want to apply, what you don't want to map, what you want to map, and so on. Cartograph is on GitHub, available, open source, of course, MIT license, like everything in OpenFE. And as an outlook, we're also thinking with the Rinica lab, for example, about how we can now go beyond what cartograph is right now and how we can solve, for example, multi-state problems. So there are methods out there, free energy methods, that do multiple end states in one simulation, and we need core regions for those multi-state simulations. So here, this is one example of our current under development branch on how we find one core region for all these ligands that you see on the right. Okay. With that, Aniket already foreshadowed there's also another project of mine, and this is actually quite dear to my heart as well. And this is called Connector. So what is Connector? Connector is now, as we have the atom mappings, which are the arrows of our graph, Connector is the part of the algorithm that kind of defines the layout of your graph. And Connector gives you a lot of algorithms, for example, like this maximal network. This is basically building the fundament of all of our approaches. This is the fully connected graph. And then usually what you do, if you have no knowledge prior, then you start to reduce this fully graph down to an MST, so minimal spanning tree, for example, or a star map. So that's why, for example, this maximal network needs to be very fast. So we parallelized it, and then we try to apply those fast algorithms then on top of this. But also Connector is trying to go beyond these very standard approaches and is also adding something like a cyclic graph, which is introducing by design n cycles for each of these molecules to the graph. Or something like a starry sky network, which is something where I will go into the details in a second. Besides those graph generating algorithms, Connector gives you also tools on how to deal with different networks. So if you can imagine it like this, you generate your free energy network for one chemical series, for example, then you generate it for another chemical series, and now you want to connect those two graphs. This is something you can do with Connector, for example. So we have merge functionality, we have concatenation functionality, and append. And also you can delete stuff, and so on. So these are quite nice toolings, but why am I actually showing that to you? Because now we can go into advanced network algorithms. An advanced network algorithm means we get a bag of compounds here, for example. We start to cluster those compounds on different clustering methods that we have implemented right now, and then build into those clusters subnetworks that might be more efficient, for example. And then we add more redundant edges on the connecting parts. So now let's concatenate those two networks with more edges than we need inside of the clusters. This is one pretty nice usage of the tools and the generator algorithms of connector, I would say. And yeah, I already mentioned that actually. You can also think about molecule diversity problems, charge changes, scaffold hopping, and multi-state approaches, where you just want to basically switch protocol types between your different clusters, for example. And also you can, if you were into algorithms, think about how to reduce the algorithmic cost of your approaches. With that, I also want to show you the application of connector, which is already ongoing, that actually Irfan just showed us. So mouse is exactly where we started to use connector. And in this bottom line part down here, you find the usage. So what we got from mouse is basically from the generative parts and the scoring. We got now 100 molecules that are very diverse. So in the first step, we started to cluster them by Morgan fingerprints into different subcategories, did shape alignments on those subcategories, and now you already see that certain scaffolds are basically appearing down here, and those we could then use in our RBFEs. And this is exactly what came out. All the clusters were now put into star maps. Those star maps were concatenated by 3 edges each. Noise clusters that we had were also added to this. And this is how we ended up with this starry sky network, which is quite an efficient and robust network in our hands, at least right now. And this resulted in those from 100 molecules, we got 92 back, and could then also compare them with ABFEs from the cluster centers on. That's exactly what Annika just told you. And with that, I'm already at my acknowledgement slide. So I want definitely to thank the great OpenFE team. It's actually really a pleasure to work with them. Many of them are here. It's also amazing to work in the ComCam group at BI and to also get all these insights into how drug design works in application parts. And with that, also thank you for your attention.
Do we have any questions?
Thank you for the talk. It's very nice. So for the 2 applications that you showed us, is there a way to quantify how challenging a transformation is going to be, something like a score for each link?
That's the intentionally left out part. But yeah, so right now in OpenFE, there's the low-map scorer, for example, which is a scorer that tries to get a number between 0 and 1, emphasized on certain rules that were defined priorly. But also in cartograph, we have other metrics like shape overlap and RMSD of the different mappings. So in theory, you can use any function that kind of gives you insights on how difficult a transformation is, right? And yeah, that's ongoing work.
Hi, Benjamin. Great talk. I think one of the challenges associated with creating a free energy perturbation map is the interpretation, especially for the more complicated graphs, can be non-trivial as well. I think at current OpenFE uses a maximum likelihood estimator to do that network understanding. Do you think you could describe a little bit about what that method does, and how that's different from other more classical hysteresis types of analyses?
I wouldn't go into that detail, to be honest, because this is the MLE approach that is implemented in Cinnabar. And this is kind of what you do in the end of everything, right? So I was focusing on setting up, and this is something you do post. We can maybe talk later about this, if that's okay.
Thank you. Yeah, fantastic talk. I was wondering on the hybrid topology part, when the cartograph does not, let's say that the parts that do not overlap, but they are chemically equivalent, they are not detected, and you see that as a disadvantage. Actually, can it be as an advantage, because those parts, maybe they are not well aligned because the 2 ligands differ, so one part is pushed, and then you want to transform it?
Absolutely, that's a very good comment, and that's also what I love to think about it. Like, imagine you have different binding modes of the same molecule, for example, and you want to do this RBFE calculation with that. And this is exactly what allows you to do that. Because if you would do an MCS, it would just be mapped onto each other. So is it a bug? I wouldn't say so. It's a feature. Ooh, very bold.
No more questions? All right. We can end this session in here and go on with the lunch. Have a good lunch.
Just